Okay, see if I can make the rest of these 9 videos. Alright, so 9.1. This is the beginning of hypothesis testing. This is the part where if you sort of figured it out, if you sort of got the vocabulary, if you knew the mechanics, then it doesn't matter now because everything's all different. You're going to look at it from the position of either a lawyer or a straight up statistician who's trying to disprove or prove something. And it's just a level of experience you guys don't have. So we'll go through it real quick, and then I'm going to give you some shortcuts to do because I don't want you to do exactly what it says in the book, which is really not a surprise. But anyway, alright, so the null hypothesis is the position of no difference. That is the point where you should start a test. This is why, if you look through these Facebook posts or a lot of these studies about vaccines causing autism, this is why they have trouble getting their studies accepted. You can't walk into a study saying, I'm going to show you guys you're wrong. It doesn't work that way. That is the ultimate goal, but it still doesn't work that way. What you need to go into your study saying, I have all these people, I have this perfect setup, I'm going to show that you guys are totally right, that there's nothing different. That's the deal with the null. No difference, nothing, no changes. So you go in there and you set it up. It's called H with a little 0, which is null, not. You guys should have enough southern background to know that not means 0. No difference. The beginning is that everything is exactly as you told me. Whatever the accepted truth is. It's I agree, I'm on your side. We're going to show all these crazy people that everything is just exactly how you say. So all of your null hypotheses have equals marks. I'm telling you this is exactly the same as what you told me. Now, the flip side is that you have an alternative hypothesis. Now, for the most case, this is actually what you want to prove. You want to go in there to prove whoever is arguing with you that they are right, everything is perfectly normal, it's all the truth, and then you do your test and your answer becomes something that is so far out in left field that you can't do anything but say, you know, I don't see how you're right because I can't show you how to make it work. And for statistics, you do that over and over and over. And every time you get a result that shows that you assume they were correct, but you just can't prove it, then what you're trying to make them do is force them to say, I think I might be wrong. You never get to say somebody's wrong in statistics. What you generally get to do is, I don't think you're right. Which is kind of, you know, I spit in your general direction. Something like that. Which is one of my favorite jokes that I don't get to say much. So anyway, when I did the problems, the first set, I just set up the null and the alternative. The null has the equals mark. The alternative either has a less than, a greater than, or not equal to. Now the book will go through less than or equal to, or greater than or equal. Forget that. Make it simple. The null has the equals mark, period. The alternative has a less than, a greater than, or not equal to. If it has a less than, then it is a left-tailed test, which means that I'm assuming that I'm going to go with the fact that you're right, that everything's the same, but when I get my answer, I think it's going to be way, way, way down on this low end. That's a left-tailed test. It's way out on the left end of things that should not happen. If you do greater than, then you get, I'm going to assume it's going to be much, much larger than what you think. It's going to be way, way out on the right end of this list of possible solutions. Not equal to means I have no idea what's going to happen, but it's going to be too little or too big or something. I'm just telling you that it's not going to be the same. That is a two-tailed test. That one is one of the easiest ones to start with and one of the hardest ones to keep. So, I set all of them up, 15 through 19. I wrote down the null, the alternative, two-tailed or right-tailed based on the sign. I made little arrows, so you should be able to look at that. You will notice that if it talked about the mean, I used the mu, the population symbol for the null. I used the sample symbol for the alternative. That is really kind of my way of reinforcing some of these symbols, which is really all you might get out of this class. When I got down to populations and proportions as opposed to means and averages, then the null gets rho, which is that funny looking P with no pointy ends, and the alternative gets P hat, which is your sample. Alright, so I did all those. Alright, now in the conclusion part, when you get to page 3 on the notes, conclusions are very simple. I do not want you to try to make the statement of saying, I say this is probably true and that. No, we're either going to reject the null or we're going to keep it. Those are your two choices the rest of the class. If it tells you your significance level is 0.05, that is 5%, which is symbolized by the little alpha, which in every class I've ever had, we've called it fish because it makes it funny. So, if the p-value you get from your test using your calculator or using me or whatever is smaller than your fish, you reject the null. If the p-value you get, and it's not rho and it's not p-hat, it's just plain old p, if the p-value you get is bigger than the fish, then you must accept the null. And this is one of my favorite little sayings. I love to write it on the board, but it's not near as funny this way. It says if the p is low, the hoe must go, which I love. It's really not politically correct, but it's still pretty funny. Alright, so then on the last set, 23 through 28, I wrote the significance value, I wrote the little alpha or the fish, then immediately underneath it I wrote the p-value that they either gave me in that chart or that I discovered some other way, and I wrote down which one was bigger or which one was smaller in some cases. So on 23, now here's something that I do that makes it easier if you're not really paying attention to your decimals. The p-value they gave me in that chart, they all have 3 decimal places. So I made sure that my significance or my fish had 3 decimal places. So 0.050. That makes it a 50. So is 50 bigger or smaller than 382? It gives me something that's easy to look at. So the 382 is larger, which means the alpha is the smaller one. You would keep the null. So 24, they gave you an alpha or a fish as a 10. Actually, they gave you a 1. Pay attention to what they're doing. So I wrote down 0.010 because I want 3 decimal places. So it's 10 bigger or smaller than 184. Then you make the decision. And you're back to 10. Is 10 bigger or smaller than 28? Then you make the decision. Then they go back to 5, which I wrote down 0.050, which gives you 50. This is why I did it. Because if I asked you, was 5 bigger or smaller than 28, 5 is smaller. But that is not what you have. What you have is 50 bigger or smaller than 28. In that case, the 28 is smaller. You would reject the null. Same deal. I wrote the alpha, the p, which one's bigger, which one's smaller. It really just depends on which one you think about, which one you want to look at. But if the p is smaller than the fish, reject the null. If the p is larger than the fish, keep the null.